Excellent. All right. So we are going to kick off our September TMN Tuesday just a few minutes before the 10 o'clock a.m. Central Hour today. We are running an early morning special with our TMN Tuesday this month, but that is because our speaker is phenomenal and worth it every change possible. So I'm going to get started with our tech check for our folks on our WebEx. If you are joining us from our Facebook, please know that we won't be able to answer your questions from Facebook Live, but we'll try and get some of those answers to you after the webinar. For the folks on our WebEx today, if you are new to our TMN Tuesday WebEx, do not worry, you cannot unmute or share your video, but that is on purpose because in many of these webinars we have hundreds if not thousands of participants, and we want to make sure that we are giving all full attention to our speaker today, Dr. Nielsen-Gammon. Again, running through our tech check just a little bit, if you are now seeing me click through slides and you're going, wait, Mary Pearl, I can see your voice move, or I can see your mouth move, but I can't hear your voice. You can't hear voice move. I need more coffee still yet this morning. But if you can't hear me and you're going, what's going on? I need you to read this screen real fast. You can't hear me telling you to read this screen, but hopefully you are making those setting adjustments now so that you can turn your volume up to be able to hear our fantastic speaker. One more second for that. All right, again, for our WebEx folks, we're going to be using the chat function today. Our Facebook Live folks, I will be checking in on that here in just a second, but we won't be able to answer your questions. For WebEx folks, again, our chat is for on-topic, professional, and respectful discussion only. Please use clear and full sentences, avoid acronyms, try your best at spelling and grammar so that Michelle and I can understand your question and interpret that to the best of our ability to our speaker today. And make sure that you're chatting to everyone so that we're all participating in the same discussion. Lastly, and I'm seeing 10:01, so I'm trying to rush through these, and I apologize. If you are still having WebEx issues, take a quick screenshot of that Help Center phone number or that WebEx link, and that will get you some more help if needed. All right, so jumping into our TMN Tuesday event this month, we have a fantastic speaker. But if you are new to our TMN Tuesday event, Michelle, do you want to talk about what TMN Tuesday is and the Master Naturalist program?
Sure. So TMN Tuesdays were started last year. On the second Tuesday of every month, we offer a live streamed and recorded advanced training session offered by the state program. You can see our schedule here on the right hand side of the screen for the rest of the year and what we've had all year. We've had some great speakers so far and even more coming up, including and especially today's. Our sessions are typically held at noon on the second Tuesday of every month, but to accommodate being able to have John Nielsen-Gammon here today, we are meeting a little bit earlier today. The recordings are available, will be available. All of our TMN Tuesdays are recorded and will be made available on our website. Typically it's the day after, once everything processes and gets posted. And the recordings are available for Master Naturalists are able to watch the recordings for advanced training credit. Yeah, the next slide. If you're new to the Master Naturalist program and this is your first TMN Tuesday, just know that you're always welcome to join us. Our mission, we're sponsored at the state level by Texas Parks and Wildlife and Texas A&M AgriLife Extension. We are a volunteer program, and we encourage you, if you're new and interested, to find a chapter near you and learn about their next training class and how to get involved.
And I'll drop that link in the chat here in just a second too.
Thank you. As a reminder, another advanced training event that we have coming on coming up real soon, and registration is open now, is our Texas Master Naturalist statewide annual meeting. This year it's held in Houston, October 20th through the 23rd, and anyone is welcome to attend that. You don't have to already be registered and involved in the Master Naturalist program. In fact, new people attending our annual meeting for the first time are always exciting to have and excited to get involved in the Master Naturalist program. So everyone's welcome. And Mary Pearl's dropped the links there for the annual meeting and registering if you want to learn more. We have over 90, almost 100 different sessions going on at the annual meeting this year.
Different sessions, yeah. A lot
in addition to tons of field trips and field experiences and trainings, field training going on throughout the weekend. Do you want me to cover the etiquette real quick?
Yes. Sorry, I could do that. I got distracted by the chat. Just a final round out of our TMN Tuesday webinar etiquette. We always like to make sure that we share this so that we're all on the same page as we're going forward in today's webinar together. Again, you cannot unmute or share your video, but that is on purpose. We are going to use our chat function today to ask questions of our speaker, and please keep that respectful, professional, and on topic. Again, Michelle already said recordings will be available, AT is available, and we'll drop the information for that in the chat as well for those folks. And then I'll also put that link on our Facebook Live for those folks joining us there. And then that leads into not taking any more time away. Michelle, you want to introduce our speaker? Oh, you're muted.
Sorry. I was so excited I started right away and didn't unmute myself. We're so excited to have John Nielsen-Gammon, who is our Texas State Climatologist, with us this morning. He is representing Texas A&M University, and his presentation this morning will be covering our summer, the drought of the year this year, what happened and why, and what will we be looking at as far as the future and our climate moving forward.
Well,
right. And with
I'll
that,
just
John,
have to tell you that. Thank you very much for that introduction. Also, thank you for that very flattering photo. I want to just give you a true image of what I actually look like now before I get into my talk, which is on what happened this summer. When I was invited to give this talk, we didn't know exactly what was going to happen, but it was already starting to be a very interesting summer, so I thought this might be a pretty good topic. And indeed, we saw drought and heat and flooding. In other words, it was a typical summer in Texas. This is what the drought looked like. This is a plot of drought conditions over the past 13 months or so. What we're looking at is the percent of Texas under certain drought categories. You saw the map earlier. The categories correspond to abnormally dry, which is not technically drought. Then we have moderate, severe, extreme, and exceptional. And things started drying out back in September of last year. It's pretty rare that the entire state does not at least have some corner of it in abnormally dry conditions. But things just steadily got worse into the winter, and then there were a couple of periods of slight improvement, but basically we ended up with over 60% of the state in extreme drought by early August before things started finally improving dramatically in mid to late August. And to put this in historical context, here's what it looks like since the drought monitor started in 2000. Frequent periods of drought. Some of these are more memorable than others. 2006, 2008 and 9, 2011, lingering on to 2015. And here's the most recent drought, which at least on this scale, in terms of how much of the state got into extreme drought or even exceptional drought, was the second most intense drought in the 21st century up to this point. In addition to drought and accompanying the drought was some extreme heat. This is a graph of every monthly temperature on record for the state of Texas going back to 1895. So I think that means there's 128 lines on this graph since it's been 128 years starting in 1895. And obviously it's cooler in the winter than it is in the summertime. I've highlighted three recent notable years. The current one is in dark red, 2022. And what you see is we peaked at a July temperature, which was actually the hottest July on record for the state of Texas, rivaled really only by 2011, which was that other drought year and exceptionally warm as well, which is not a coincidence, as we'll see. We were also the hottest or second hottest May on record, and if you look at, say, the whole period from April through August, um, we were either the hottest or second hottest compared to 2011 on average over that whole period. Last year, summer was quite a bit milder, but there was still some unusual weather last year, like this thing over here. This is not a typographical error. Someone didn't accidentally enter 59 degrees when they meant 49 degrees. That was December of 2021, which you may or may not still remember as being nice and warm December, but on this plot we see it as the most unusual month for temperatures in the history of Texas record keeping. There are a few other somewhat unusual years where the curve sort of stands out a bit, but like 2017, the year in which spring came 1 month early to Texas. But this is really an amazing anomaly. And you look at this, and I was thinking, I wonder what the odds were of getting something so ridiculously warm. Um, Using standard statistical takes, it would probably come out to odds of 1 in 10,000 or something like that. Except I dug back into the history records for Texas, and even though we don't have a statewide value, for the stations that were operating back in 1889, temperatures were actually comparable. In both cases, we made it basically through almost the entire month without getting a cold front. And so while it's extremely rare, it actually has happened before. Okay, well, in addition to, well, 2022 and 2011 are all both looking fairly hot, but that's partly drought conditions. Now, let's talk about, I guess I'm supposed to be giving you the why of the summer, and asking why questions about the weather is always a tricky topic. As you know from talking to small children, uh, the answer to a why question often leads to another why question, and so forth. And it's never clear, even when adults are asking about why'd this happen with the weather, what sort of answer they want. Why did it rain? Well, because water fell from a cloud overhead. That's an accurate why answer. Why did it rain? Because the Earth is at a temperature in which water can exist both in solid, liquid, and gas form. That's an adequate answer to the why question, but it may not be what you want either. So I'll try to give good why answers, but it may not be the answer you really think is explanatory. Well, one why for why it was so hot last summer was because it's getting hotter. This is a plot of annual average temperatures in Texas over the past, again, 128 years. And you can see that temperatures have been rising since the 1970s at a fairly steady pace, not unlike the rate at which global temperatures are rising, and not coincidentally either. And indeed, what you see here is that we have not had a single year in the 21st century as cold as an average year in the 20th century. And as temperatures continue to rise, it becomes increasingly likely that we'll ever do so. So that's a remarkable Texas-focused climate change statistic that um, every year in the 21st century is likely to be warmer than any typical year in the 20th century. And the reason we can say that sort of thing is because the variability of temperatures from year to year is only a couple of degrees, and temperatures are already a couple of degrees warmer than they were in the 20th century. If we look at individual months, basically we have a lot more variability. It can have a range of 8 degrees between different uh, months. And so this plot of July temperature still shows us being about 2 degrees warmer than the 20th century average, but it's still not unheard of to have an individual month cooler than what would be typical in the 20th century. In fact, we had that last year. But as this continues, if you just extrapolate it outward, it looks like in another couple decades, we will have put the 20th century well behind us in terms of typical weather. Now, so that only gets us basically 1 or 2 degrees of increased temperature. So in that sense, climate change has contributed directly to this past summer being a hot one. But on the other hand, did climate change contribute to last summer being a cool one? Well, actually, climate change contributed to being, say, not as cool as it might have been in the absence of climate change. So, climate change is changing the odds and what's typical under a given set of weather circumstances, but climate change is not determining the weather circumstances. So, let's look at the weather circumstance that led to um, the high temperatures. And they're basically um, 2 of them. One is it was fairly dry this summer, and the other is it was fairly dry during last spring and last winter and the previous fall. Now, we don't have a whole lot of years in the climate record in Texas that were dry during all of those times. So what I'm showing you here is output from climate model simulations to look at how temperature and rainfall uh, influence each other in Texas. So first off, um, all of these dots are comparing the precipitation compared to normal during the summertime versus the temperature compared to normal during the summertime. And what you see is if it's dry, it tends to be hot. If it's wet, it tends to be cool. We saw that this past year, for example. One reason for that would be that if it's raining, it's also cloudy, and clouds are pretty nice at keeping temperatures low. In fact, another bit of Texas climate trivia for you. The wettest summer week in Houston history was the coldest summer week in Houston history was Hurricane Harvey. The average temperature over that week was lower than the average temperature over any historical week during the summertime in the past. So dry, sunny, hot, those things all go together. But then the color coding is looking at whether it was a wet preceding period, the preceding fall, winter, spring, or when it was dry. Green is wet, and as you can see, basically it's typically about a degree and a half Celsius cooler if you start off with preceding period being wet and that the preceding period is dry. 1.5 degrees Celsius is like 2 to 3 degrees Fahrenheit. And the reason for that is rainfall makes the soil moist. And when wet soil receives sunlight, some of that water evaporates. And plants evaporate water as well if they transpire it, drawing it up through their roots. And it takes energy to evaporate water. And if you don't have any water to evaporate, all of the sun's energy is going to go into heating the ground. And so that partitioning between heat and evaporation determines why, if the ground is dry, it's going to end up being hotter in the summertime. Here's another plot of the same sort of thing. Now we're actually looking at actual observations, and I've been keeping this plot up to date since 2011, when we had the hottest, driest summer on record, looking at total rainfall and average temperature. And the colored dots are everything since the year 2000. It's remarkable to see that basically those points are all in the top half of the envelope of historical points, meaning climate change really hasn't shifted these points over to the left or to the right very much, but they've shifted them sort of diagonally. So a given rainfall amount is going to lead to higher temperatures, or correspond to higher temperatures now than it did in the past due to climate change. We've also actually seen an increase of rainfall on average, so we do have a bit larger number of points over to the right than we did to the left, which has actually helped to moderate the summertime temperatures a bit. Here's 2022. We came out with the second hottest summer on record. The point is out here mainly because we had so much rain during late August. If late August had been normal, we would have been hotter and drier. The point maybe would have been somewhere over here. But you can see how important it is, a certain amount of rainfall corresponding to a certain summertime temperature. Okay, to the extent that climate change is affecting these temperatures and is going to in the future, we can compare climate model simulations here in blue with historical observed trends in Texas. And what we see since 1950 is the trends are fairly similar. Since 1975, the trends are fairly similar. And the projection over the next couple of decades is for the future trend to be similar to the trend that we've seen over the past 40 years or so. So we can look at that trend on a map, and temperatures have been going up throughout the state of Texas. It's not just urban areas, obviously. It's not just rural areas, although you can find urban areas that have gone up larger than their surroundings. Surroundings are getting warmer too. And that's a description of what's going on with average temperatures. That's true for average maximum temperatures. Oh, but by the way, before I go on much farther, this particular set of plots that I'm showing is from our report on extreme weather trends in Texas, and I'm going to drop the link into the chat right now in case you want to look at some of these graphics in more detail or read about them. But in any case, we're seeing maximum temperatures rising since the 70s. We're seeing daily minimum temperatures rising since the 70s. About the only thing that hasn't risen dramatically is the average hottest monthly temperature in the summertime. That was quite a bit hotter in the early part of the 20th century than in the latter part. And we don't have a conclusive explanation for that particular statistic. My guess is that that relates to a large increase in the amount of agricultural irrigation and surface reservoirs that took place during the 1950s to 1970s, which makes it guarantees that no matter how hot and dry it gets, there's still going to be a decent amount of evaporation going on somewhere in the state to limit the extent of extreme high temperatures. And it's not that summers are getting colder, because if you look at the coldest day of July or August, that's going up along with everything else. So in a sense, you could say that we're losing the cool respite days in the middle of the summer. They're more persistently hot than they used to be. By the way, we had an interesting weather event back in February of 2021 that y'all may have noticed. The extreme cold. Here's a plot of the coldest temperature of the year, and yeah, sure enough, it shows up as being pretty dramatically cold, on a par with 1989, and not quite as cold as February of 1899, which was saw more than half the state drop below 0 degrees Fahrenheit. Uh, Trends are like the trends for the other temperature plots. We're warmer now than we were in the 20th century by about a couple of degrees. So in fact, at least extreme cold is getting warmer along with everything else. Um, and this plot also points out why perhaps the grid has such difficulties during that event. It was exceptionally cold, but what really stands out to me is that we'd gone like 30 years without any of these, let's call them seriously cold events, where the temperature got down to the single digits on average in the state of Texas. We were having like one or couple every decade until 1990, and then we didn't have any of them. And it's not climate change that stopped that. If you work in the climate change trend, well, okay, we sort of had a couple of marginal ones maybe, but still, the grid had not been stressed with extreme cold. The natural environment had not been stressed with extreme cold. So, cold intolerant plants, for example, were able to creep northward and make quite a bit of progress until this sudden shock of 2021. And we should expect to see some more cold in the future, and it'll feel like a cooling trend, but that's just because we were so ridiculously lucky back here in the preceding 30 years not to get cold. Now, so that's part of what was special about this year. That it was actually not special. That's part of a warming trend. But why was it warmer than the trend even? And the standard answer for that would be La Nina. This is a plot of average temperatures in the tropical Pacific right now compared to normal. You can see Central America, South America, and Australia on this plot, and the blues are cooler than normal. When this large patch of the ocean is below about half a degree Celsius from normal for several months, that counts as a La Nina. And we're in a La Nina right now. We've been in a La Nina for the past couple of years. And the forecast is that La Nina is likely to be the case all the way through to sometime January, February, March of next year. And La Nina affects the weather patterns around the globe to a considerable extent. This is the typical conditions experienced in the wintertime during La Nina. It's cool in the tropical Pacific. That's the definition of a La Nina. It's also dry in the tropical Pacific and wet farther west. And that's basically the mechanism by which the rest of the world is affected, because it's essentially changing the circulation patterns around the globe by altering where you've got thunderstorm activity, where you've got ascending air, where you've got descending air. You're moving the jet stream around, and that, at least in the United States, moves the jet stream north, and means that you get stormier weather in the northern United States, and we tend to be warmer and drier. we're actually the only part of the world that's particularly warm and dry during a La Nina. So kind of special in that regard. If you look at the La Nina or El Nino conditions, as I mentioned, anything more than a half a degree Celsius below normal in the tropical Pacific is La Nina. Compare that to our rainfall during November through March. It's a pretty strong correlation. El Nino tends to be wetter, La Nina tends to be drier. And the orange dots are basically the past 12 years or so. 2011 was a particularly strong La Nina. It was also particularly dry. 2022, La Nina, dry. 2021, La Nina, not as dry, but about as dry as would normally be expected during a La Nina. So La Nina explains why these years tend to be dry. It doesn't explain why 2022 was only 4.5 inches average statewide rather than 6.5 inches, but it made dry conditions certainly more likely. So that's part of the explanation there also. Now, this is November through March because that's the time of year La Nina has a big effect on our rainfall. Uh, the it doesn't explain why it was so dry during the summertime also. And for that, I'm gonna look at the weather patterns that we had during the summertime. This is a plot of the weather patterns in the upper troposphere. We talk about atmospheric ridges, building, and so forth. We're talking about things in the upper troposphere in that circumstance. And when we have the height of pressure surfaces up there being especially high, we tend to be particularly dry. And here we were with the Central United States in June, having a big upper level high on top of us. Here we are in July, having an upper level high on top of us. And here we are in August with the upper level high moved off to the Pacific Northwest and Western Canada. So the upper level weather patterns were working against us in June and July, and were much more favorable in August. At low levels, basically whether or not we get thunderstorms often depends upon whether moist and humid air can ascend past the middle of the troposphere air, like a couple miles above the Earth's surface. If that air has been heated by the desert Southwest, it's going to prevent thunderstorms. If it's just purely tropical air, then we can have plenty of thunderstorm activity. Well, here's the wind pattern during June. We basically had this circulation pattern where air would move over the desert area of West Texas and New Mexico, circle around and come back on top of us and just stay nice and hot, unfortunately. The pattern in July is similar. You can see the circulation going from New Mexico north of us, across Alabama, and back across the Gulf of Mexico, keeping the high pressure on top of us and keeping the air dry. And then the big change is here in August, where instead of having a circulation system on top of us, we are getting a direct conduit of tropical air coming across the Caribbean, Gulf of Mexico, and into Texas, so that basically the lid is off on the convection and we can have thunderstorm activity, which we saw persistently from about August 20th or August 10th all the way through to the end of the month. Okay, so that sort of accounts to why 2022 we had drought developing during the winter. It accounts to some extent why we had drought persisting in the summer, at least until August, and we still have drought in Texas because August rains wasn't enough to end a year-long drought. But climate change also affects drought as well. This is a plot of projections from global climate models of what's uh, likely to happen with respect to drought in West Texas. In East Texas, this plot is similar to this. Essentially, we're looking at um, average soil moisture conditions. The green line is soil moisture in the top uh, foot of soil. And it was humming along nicely until about the year 2000. After that, it's projected to decline fairly steadily. Interannual variability would still be fairly large. Interannual variability would get you between like -2 and +2. So this is basically saying you're going to be more likely to have dry conditions than wet conditions going forward, at least when you look at things like soil moisture. And one possible reason for that would be a decline in rainfall. There was a study recently that looked at the mega drought in the Southwest and to see whether that was rainfall or something else causing it. And it was an interesting study, so I want to highlight it because it has some lessons for Texas. So focusing here on panel E in the upper left, the black is the estimate of actual soil moisture conditions in the Southwest United States, which were, it was nice and wet in the 1920s when they divided up the Colorado River into different states. It was nice and wet in the 80s and 90s, and then it's been dry since then, in fact, drier than any previous historical condition. Now, climate model average simulations of rainfall and its rainfall's effect on soil moisture are shown here in the thin lines, and then the average is the purple line in the middle. And they don't have these big swings because we're looking at averages across different weather conditions. There's no way a climate model is going to predict exactly when it would be wet, when it would be dry. So we're looking at the overall trends here. The overall trend is for getting wetter based on precipitation alone. Precipitation is projected to increase in these models. But now if you, as a computer model, we can play games with it. We can hold the precipitation constant and allow the temperature to vary by itself and relative humidity. And those show a dramatic decrease of soil moisture. So that's saying that the climate change in soil moisture in the West, according to the models, is going to be caused by higher temperatures rather than decreased rainfall. Decreased rainfall actually gives us a range of possibilities, but the increase in temperature gives us decline in the trend. CMIP 5 is the set of climate models that's being used in this study. So presumably the same thing could happen in Texas. Increase in temperature would lead to a decrease in soil moisture. Also, by the way, if you get larger variations in rainfall from month to month, you'll tend to see drier conditions picking up more frequently. And if you get a change in the rainfall pattern so that you get more in the winter and less in the summer, that's going to increase drought conditions because things tend to dry out mainly during the summertime. And all of those things are projected to occur. Temperature definitely, these other changes in rainfall maybe. Meanwhile, this particular factor here, changes in the water use efficiency by plants. What that is the increase in carbon dioxide means that plants don't need to open their stomata as much to take in the carbon dioxide they need to grow. And that means they don't lose as much water through transpiration while they're doing so. In other words, they can grow as much with less water. And so that would mean that plants are able to leave more water in the ground. And so that could be a trend for counteracting the drying that we're seeing due to rising temperatures. And there are a few factors that I put in the essentially could go either way side. Annual rainfall. We've seen an annual increase in rainfall in Texas, about 10% over the past century. Climate models tend to project a slight decrease, but with a wide range of possibilities. So it's not clear how future rainfall is going to change. Now, individual rainfall events are becoming more intense. I'll show you a little bit of that in a moment. And that means that you actually tend to have less opportunity for rain to soak into the soil. And if plants respond to being more efficient by growing more, then maybe you end up with as much evapotranspiration as you had before anyhow. So it's not clear how that's going to affect things. So let's look at some of these particular rainfall trends. First off, model projected trends in precipitation. The colors give you the trend in percent per decade. As I mentioned, we've gone up by about 1% per decade over the past century. So that would get us into the second green color historically. But the model projections are for a drying trend. But this hatching means that at least a quarter of the models disagree and say that it could be wetter. So it's not really clear what's going to happen with rainfall. Evaporation changes are about the same because basically you can't evaporate more water than you get from rainfall. So those trends sort of go hand in hand. What the higher temperatures do is make water evaporate sooner, so that that leads to soil moisture being drier on average. And in fact, here's the projected soil moisture in this set of models. And indeed, Texas is not unique. Almost the entire United States is consistently projected to have a drying trend of soil moisture of 1 or 2% per decade. Both the topsoil and the entire soil column, at least for Texas. But runoff is projected to probably increase by a substantial amount, although there are some models that disagree with this and say it should decrease. So what does an increase of runoff mean for drought? Well, it means potentially more stream flow on average. But it doesn't necessarily mean that a typical day will have greater stream flow, greater river flow. It probably means that the peaks of stream flow will be higher because this is being produced by that increase of intense rainfall. More intense rainfall runs off rather than soaking into the soil, so it contributes to the decline of soil moisture and it contributes to the increase of runoff. For water supply, by the way, that's good news for surface water supplies because there's more water going into reservoirs. That water may evaporate more rapidly once it's there. It's probably bad news for aquifers because aquifers get their water through the soil. If the soil is drier, then the aquifers aren't getting as much recharge. You can imagine that this sort of change would also exaggerate the difference between upland plants and riparian environments as the higher terrain becomes drier and the river bottoms potentially become wetter. Lastly, just for a couple minutes before we take questions, I want to talk about that extreme rainfall in particular. We had some impressive rainfall throughout the state. If there are some of you from the Dallas area, you'd doubtless be willing to talk about the rainfall we got in August 22 and 23. This is data from the CoCoRaHS network, which is a network of volunteer rain observers, which you're welcome to participate in and get credit for in the Texas Master Naturalist program. And we see several observers reporting a foot or more of rainfall across central Tarrant County, central Dallas County, and some high totals extending down into Ellis and Coffin County as well. So, hey, 12 and inches of rain is not too shabby. How does that stack up in the context of the largest single-day rainfall events on record in north central Texas? Well, it doesn't even make the top 10. Albany in 1978 is the poster child for an outlier. This was the remnants of a tropical storm that managed to produce a series of thunderstorms right over Albany. If you go back to 2015, the flooding in Corsicana, 19 inches of rain was the peak one-day total. There were 11 stations in the area that received at least 10 inches of rain in a single day. Go back to 2010 for some heavy rain farther south that was fairly widespread in the area between Temple and Austin. And okay, for a single day total, this ranks tied for 15. So even though it's it was a 100-year or more rainfall event in terms of very rare in any given location, we see rainfall events like that on occasion in the region. And so it really doesn't stand out as being historical in the context of Texas, although it was fairly historical for Dallas-Fort Worth. And as people in Houston will tell you, extreme rainfall is much more common and much more intense in the Houston area than the Dallas area. The amount of rain you'd expect to get once every 100 years in the Dallas area is around 10 inches, whereas the amount you expect to get in the Houston area is around 15 inches. So it takes a lot more rain to raise eyebrows in Houston than it does in Dallas. And by the way, we did our own trend estimates of this. Rainfall is increasing on average across all the southern and southeast United States. This is trends in intense rainfall. This averages out to about an 11% increase in intensity over the past 40 years. And that, in terms of how frequently these events occur, it represents almost a doubling of the frequency of extreme rainfall of like 10 inches or more. So, give you a summary so far. So it was mostly a hot and dry summer. That mostly, of course, means that when you don't have drought, you have floods, unfortunately. Climate change did make the summer hotter. La Nina contributed to making it hotter and drier, and the weather patterns during the summertime were basically the final nail in the coffin that made it a particularly hot summer, almost threatening 2011 until the weather patterns changed in August. And lastly, droughts in general are changing, but they're changing in a complex way. It's not like we're going to get less rain, although we might. It's more like all the other things that go along with droughts are changing, and the impacts depend on what type of drought you're actually talking about. So thanks for your attention. I'll go ahead and stop sharing now and be happy to answer questions.
Thanks, John. I had a question on the third to last slide. You talked about the changing frequency and these 100-year drought conditions or 100-year rainfall events. It wasn't drought. 100-year rainfall conditions. So is it fair to say that when we hear on the news that there's a 100-year rainfall event that's occurred, we should cut that in half at this point?
Yeah, 100-year compared to historical conditions, but we should expect them to be happening more frequently now. So yeah, realistically, the odds of that sort of event present day is about almost twice as high as it used to be. So yeah, if you want to do it that way, go for it. Hopefully in a few years, we'll actually be assessing those odds, taking climate change into account so that you won't have to do that mental calculation anymore. It'll be already factored in.
Well, we've got some great questions coming in from chat. Michelle, do you have one that you want to ask first, or I've been watching a few of them.
I'd suggest just start at the top of the list, but if you had some you wanted to specifically mention, go ahead.
Came in that I thought was pretty interesting, and you spoke a bit to it. Skip asked, Doesn't larger storms and extended rainfall imply larger runoff levels, contributing to freeing up natural loss of ambient water in the soil? And then I'd add to that a changing plant dynamics with this lowering soil moisture factor that you were mentioning in West Texas.
Yeah, we, well, I don't know what freeing up loss of ambient water really means in that question. We get larger runoff and consequently less water soaking into the ground. And it's not, look, I don't have to mute my phone. And it's not so that there's less in the ground in the first place. Now, if you do have an extended rainfall event, then great. Then you have time for stuff to soak into the ground. But we don't actually expect rainfall to become longer. In fact, if you have the same amount of rain and it's more intense, it's going to be shorter. So we actually expect to see, and we have seen, at least on a larger scale, a decrease in the number of rainy days.
Mm-hmm.
So I don't know if I've circled around to answering the question or not.
No, I think that was and that was a question that actually Glenn had asked earlier if there was a noticeable trend in the number of rainy days. So you just answered his question as well.
Okay. Now, by the way, if you want to think of what all this means for flooding, say, starting off with lower soil moisture means that you can tolerate a bit more rainfall before producing the same amount of flooding. So that could mean that more common floods actually become less common. But on the other hand, if you get one of these super rainfall events where it doesn't really, where the amount that soaks into the soil is a relatively small fraction of the total amount of rainfall, those floods could actually increase in intensity.
Okay. Some more questions are coming in, and we certainly aren't going to have time for all of them, so I'm going to cherry pick, Michelle, if that's all right, unless you've got any that you want to ask. I saw one in here as we're kind of launching. We're 13 days into hurricane season officially. I believe. I think it's September 1st is hurricane season.
Hurricane season started in June 1st.
Oh gosh. Okay.
The peak time of the season is basically the first 3 weeks of September.
And so the question is, what is your opinion on why the hurricane season seemed milder lately?
Yeah, I've been asked that, and my answer is I don't know. I don't actually follow the tropical weather in the Pacific, in the Atlantic, very closely. I could say that the sort of like La Nina, the odds favored more active season, but then the weather patterns are going to determine what actually happens. And somehow or another, the weather patterns have been essentially working in our favor.
Michelle, do you have a question? Okay. I'll keep asking. Robin and David asked, I've always wondered about the effects of record keeping. Is the quality and density of our weather recording stations skewing statistics, in your opinion?
Well, if you don't take it into account, it can skew it. So, for example, that listing of extreme rainfall events in North Texas, there's more recently, partly because we have more people observing rainfall. But but you can deal with that by excluding the volunteer networks and going back and only looking at stations that are long-term or stations that are persistent. So we can deal with that sort of thing. For example, the trend analysis that I did was not looking at it was looking at basically a composite single station analysis over each county in the southern United States, so that we're taking basically single records that were long periods. So certainly we hear about extremes more, and we can observe. We're more likely to get an observation near the peak of the extreme, and that will sort of skew the public perceptions. It might skew the reporting, but scientists do take that into account when they're looking at these trends.
And I apologize, these questions are all over the place, but there's a lot of them coming in, so I'm picking them as quick as I can. Marty asked, please comment on the impact of the trend of the PDO and AMO on Texas weather. And I don't know what those acronyms stand for. You probably.
Yeah, PDO, Pacific Decadal Oscillation, AMO, Atlantic Multi-Decadal Oscillation. So they're both temperature patterns that have time scales of like decades rather than years like El Nino and La Nina. And they affect our weather in similar sorts of ways as El Nino and La Nina. Scientists have actually moved away from talking them as oscillations and regarding them more as just sort of slow variations. But PDO tends to have a similar effect as El Nino, and mainly has an effect in the winter and spring. The Atlantic one has an effect mainly in the summer and fall. Back in about 10 years ago, they were both working toward drier conditions. Now one's sort of working toward drier, one's working toward wetter, and unfortunately, neither of them is especially predictable, so we can't use them to really say what's going to happen over the next decade.
Okay. Some more questions. Bob asked, has Saharan dust increasingly affected precipitation negatively in Texas or parts of Texas? The effect was very noticeable in the Houston area.
Yeah, we do get occasional years with large Saharan dust. I'm not aware that Saharan dust is increasing in general, but it can affect our weather in a couple of ways. First of all, it's a marker for Saharan air, which tends to be drier. It also affects the ability to form clouds and form rainfall. So it does tend to make our conditions drier when we do get a Saharan dust episode.
Okay. Michelle, I've lost my place on questions. Do you have one?
Hold on. Did we answer the one about do we expect more thunderstorm days versus rainy days?
I don't know actually. The thing about, we may see more thunderstorms in the sense of our weather becoming slightly more tropical as the jet stream moves farther north, which is supposed to edge farther north with climate change. But not necessarily. I mean, but all types of rain are going to become more intense. Even wintertime rain events are supposed to become more intense because it's just temperatures are going to be warmer when they happen, no matter what.
Here's an interesting question, and I'm unaware of this. Michelle asks, do you foresee any effect in global weather change from the Tonga eruption?
That eruption didn't, as far as I know, put a lot of sulfur dioxide into the stratosphere, which is the main way by which volcanoes affect our climate. They put a lot of aerosols in the stratosphere that sort of blocks sunlight and lowers global temperatures and changes weather patterns a bit. Fortunately, that eruption was like a brief 1 or 2 day event, so it didn't have a lot of time to pump a lot of stuff into the stratosphere. So probably not any effect other than something that can be detected if you look real hard enough.
Well, I've got one more question as we kind of get close to the end here, and
One too.
before I do, Lynn mentioned that you are the Neil deGrasse Tyson of climatology. So very laudy compliment for you there. And Sandra asked an interesting question thinking about the longevity of data. And it's interesting that Master Naturalists are really digging into that kind of specifics on the data. Sandra asked, since your graph and your data collection has a 28-year kind of time period, what does it look like as you look to predict future years based off of the information that we have on this very small piece of kind of Earth's history or recent history.
Yeah, you can it, the you can extrapolate trends forward a limited period of time as long as you have confidence that these are physically connected. There's a reason for those trends happening that's related to climate change. You wouldn't want to take just any old trend and say, well, obviously it's happened for 30 years, so it's going to keep happening. I haven't gotten into the details of all the stuff I talked about, but that's going into it. And just in general, for climate change, the next 30 years are going to have a similar trend as the past few decades, because any changes we make that are significant in terms of carbon dioxide and so forth mainly are going to be reflected in temperature differences over the latter part of the 21st century. Doesn't really start getting noticeable until that point. Just, but as the example from extreme cold illustrates, the trend I'm talking about is unfortunately the trend in expected conditions. You can go through a period where you have really unusual conditions, like a lack of cold for 30 decades, or extreme rainfall in Houston during Harvey. And saying that extreme rainfall is getting worse doesn't mean the next storm is going to be even worse than Harvey. It's the climate trend rather than the weather trend that we're talking about.
John, I have one final question, maybe to wrap it up and sum up today. You mentioned CoCoRaHS as one thing that Master Naturalists can contribute to, or other volunteers can contribute to. What are maybe a couple other projects or programs how else can our volunteers help or contribute to the science of this? And then what are some things that we all can do in our everyday lives?
Well, so we've got CoCoRaHS is the ability to make the weather observations, but along with that, they also have a mechanism by basically providing plain text descriptions of conditions. They also do coordinated days in which you take photographs of the environment to show how vegetation responded to conditions and so forth. And in fact, the drought monitor has a mechanism by which you can put in what you're currently observing in terms of whether there's drought or not drought in a particular area, in terms of how you're seeing effects showing up. So there are a lot of mechanisms for that. There's a program run out of Great Britain called Weather at Home, where basically you allow you upload an app to your PC, and when you're not using your computer, it runs climate models. Very simple climate models, but you can run a lot of different places and a lot of different times, and average across weather and learn some things. And that's been used in several interesting publications. So you can actually become a climate modeler if you'd like to. Once again, that's Weather at Home, with the @ being the @ symbol.
All right. I think we're up against a time crunch for you. You have a class to teach.
Yeah, I've got some graduate students waiting for me now.
Oh.
Well, thank you so much for sharing with us today, and for helping our Master Naturalists kind of see the larger picture and some of these trends. As mentioned before, our recording will be posted on our website, and I'm also going to take that link of the weather extremes document that you shared, and I'm going to put that on the website if you don't mind as well.
Okay, great.
Thank you once again, John.
Yes, thank you. Really appreciate it. Y'all have a great day. Thank you.
Sure.